Welcome everybody to 52 Living Ideas. Today is Monday, so it's the Switch Monday. As always, it's a pleasure to have Chase and Alex interview different people. Today is very special. Stacy, uh, Chase's dad, is here, and he's a mathematician, and that's one of my favorite topics. So I'm extremely eager to listen to Stacy talk about mathematics. So with that, over to you, Chase.
All right. I, I I like to introduce him as software architect by day, mathematician by night. Cool. All right, we'll go ahead and get started with the podcast. Those of you who have been here before know that I like to start things off with a quote. This one is from Brian Greene. Over the centuries, monumental upheavals in science have emerged time and again from following the leads set out by mathematics. And with that, I would like to introduce our guest for this episode of The Switch, my dad, Stacy Harris. Dad, welcome to The Switch.
Thank you very much. It's good to be here.
So, I want to get into mathematics, but as much as you may resist, I do want to hear some of your story. So, please, if you would, the way that I typically like to introduce this is if you were to divide your life into epochs, relating to mathematics in this case, if you'd like, and you could divide it into where I was before and where I am now, how would you define how you got here from there?
Okay, well, that's interesting. I did talk about this a little bit on a previous episode, but just to give background for people who didn't hear that, or maybe a different perspective on it. And some of it is mathematical, some is not. But I started life. If I were to divide things up, I would say there was my pre 8th grade self. That self that I remember. I remember some of the stuff when I was a little kid, but that was the sort of bookish, shy kid, super shy. In fact, I always tell a story. My grandmother used to send us to the corner store, and back then she could write out a note for the person who worked at the corner store, give us some money, and send us kids to the store for her to pick up things. And I was so shy that I would be speechless and sweaty, like just trying to count the change or make sure that I got all of her stuff because I was so afraid of external people. At home, however, I was a clown. I was a cut up. I did voices and accents and, silly kid at home, but in public, super shy. And always reading. I read lots and lots and lots of fiction. I was reading Shakespeare. I was reading science fiction. I was reading physics books. I used to go to the library, the Detroit Public Library, get on the bus, go to the library, and read books on computers and math. And then I would go into the arts and literature section and just pick up some giant book and read Spencer's the Fairy Queen. It didn't matter what I was reading. It all kind of made sense in the same way to me. And in fact, I talk to people about how I think about mathematics is in a linguistic way. I do have some visual kind of thinking for mathematics as well. Mostly that's when I'm explaining it to other people, but for me, it's all linguistic. Same way I think about programming, since you mentioned programmer by day. But again, super shy. Well, in the 8th grade, my sisters were in an all-girls Catholic school. We went to Catholic schools most of our lives, and they needed some boys to be in the play, and I volunteered. And of course, my mother said, "You're crazy," because I was so super shy. Why was I volunteering to be in this play? And I loved it. Loved being on stage, loved acting, thought that that's what I wanted to do because I didn't really think I was much good at anything else. Even though, okay, here's a weird one. I read a book called Half Spacesuit Will Travel. And in this book, there's a kid who wins a spacesuit, he puts it together, gets it working, and then boom, a spaceship shows up and takes him off to Mars or something. And they calculate, the kid is doing the calculation on a slide rule for how long it's going to take him to get to Mars, assuming 8 Gs and all this other stuff. I did the calculation along with him on a slide rule. And I taught myself to use a slide rule so I could be like the kid in that book. Right? No one uses slide rules anymore, but I taught myself to do it because I wanted to be like that. That's how kind of goofy I am. So doing math like that, and I even mentioned, I think in 8th grade, we were learning about square roots, and our teacher said, oh, you can't take the square root of a negative number. And I figured out how to do it. So this will be, some people remember this story. I figured out a way to do it in what I called contrapositive numbers because I didn't know any better. And I went to school excited and told my teacher, and she said, oh yeah, you'll learn about those. They're called imaginary numbers. That's nothing new. So imagine, and I was a young 8th grader because I had skipped a grade and I had started school young. Imagine that you're a young kid and that's the response you get is, oh yeah, you're going to learn about that. Not the response of, oh my goodness, you're going to learn about that, but that's great. You did an excellent job. Let's investigate more. Let's dig deeper into what you figured out. Not very encouraging, right? And in fact, I didn't get much encouragement at all. I was pretty much told not to pursue math because it just didn't fit for someone of my disposition and my skin tone, basically. It was kind of ridiculous. But a lot of the other kids were encouraged, boys mostly, encouraged to really push and go into and study math and be good at it. So I thought that was kind of a strange thing. But in my head, it was always, well, I'm geeking out over this stuff. I like this stuff. Star Trek fan. I wanted to be like Spock at one point, but in my head, it was, oh, I'm just not good at math. So that was sort of the first era, and I kind of discovered, oh, I want to be an actor. So when I went to high school, I was gonna study theater, be an actor, and I did. I actually did a bunch of community theater and studied some stuff. But I hooked up with some people. A really good friend of mine who really was also another sort of great mathematician, way smarter than I am, and we started doing stuff together. And I had a teacher. Oh, actually, so I missed something. I had a teacher in 9th grade who, so this was actually, I mixed up a few things, but in 9th grade, I had a teacher who gave me back an algebra or pre-algebra test, whatever it was, and said, hey, you're really good at this, but your calculations were off. You need to get a calculator. And I said, well, my problem is I'm just not good at math. He said, no, you get the concepts. Like you're understanding algebra, but your arithmetic is terrible. And that's kind of funny. You think about a mathematician who has terrible arithmetic, but actually there's very little arithmetic that I do in mathematics. Like I'm doing a little bit here and there, but there's a lot of other things that go on. So I told him, hey, but the problem is I don't do arithmetic the way that other people do. Like if I give you 2 numbers to multiply, you're going to write them down, and then you're going to start on the right-hand side, and you're going to work your way over to the left, and you're going to carry a bunch of stuff. And I did mine left to right. And he said, oh yeah, that's the Russian peasant algorithm. It's fine. It helps so you don't have to have a whole bunch of intermediate results in your head. Just keep doing it that way if that's the way you do it. But you can also use a calculator if you want. So I thought, wait a minute, this is crazy. How cool is this? And I really blossomed in his class, and really started to appreciate and started to do like a lot more math on my own and more advanced math on my own. And in 10th grade, when I met this friend of mine, we started doing stuff together. We did I think a pre-calculus class, it might have been, and the 2 of us decided that going to the library and studying was better. So we ended up doing like most of the homework, if not all of the homework for that semester, and turning it in. And the teacher said, oh, no, you didn't have to do all of it. I just wanted you to do the first assignment. We know, but we wanted to get ahead of the curve because we want to like learn some of the more advanced things. And she was a pretty amazing teacher too. And I actually met her later in life in college. She moved on to being a college professor. But it got to the point where we were doing so much of the stuff together, people called us the Wizard Twins, even though we looked nothing alike, and definitely not twins. But we really, really loved each other, loved doing math together, learned about computers together, all of these things. But I still had in my head that I was going to go into theater. So when I graduated high school, went to college, I decided to double major in theater and physics. I had also I advanced placed in math, in English, and in physics. And so my freshman workload was going to be a little bit easier. But I decided, yeah, I'll do theater and physics. And if you know anything about either of those, it's a ridiculous idea, because theater is lots of rehearsals, lots of time spent walking around, memorizing things, learning scripts. Physics is lots of time, especially, well, if you're doing experimental physics, which we all kind of had to do, even though I'm more of a theoretician, in labs, doing physics labs and, accelerating particles and whatnot. And so I would kind of toggle between the two, all the while taking lots of math classes. And I found that after a couple of semesters, I was adding more pure math, sometimes people call it pure or abstract math, classes into my workload. So era 3 in my life after theater was, I guess era 3.5 or 4, depending on how you count it, was, hey, I'm doing all of this abstract math. Why don't I just dump the other workloads and just get a degree in math? And I found that I just really, really grooved on that more than anything else. So I ended up switching schools. I had been going to Wayne State for a while, and then and that's in Detroit for folks who don't know. I went to University of Michigan, Ann Arbor, and moved in with my best friend, who was the other half of the Wizard Twin, and we were doing a bunch of math classes and things together. So I guess those are the sort of eras. Then post-school, I decided that, hey, I need to make money, and I was getting married. So with basically no computer science training under my belt, I had done a bunch on my own, but nothing formal. I had one formal class that my roommate and I took. It was an AI course in Lisp. Lisp is a programming language. I decided to apply for a co-op job at Ameritech. Actually, it was Michigan Bell at the time, but Ameritech, to finish up my last couple of semesters and make some money doing programming. And so I went in, and they gave me a summer assignment to do some programming. And so the first program I wrote was to do prime factorizations of numbers using a language called COBOL, which is an utterly ridiculous thing to do, because COBOL is a business language, but they wanted me to write something that would be what's called a benchmark, basically a massive test of this language, this computer language, the compiler for it. And if I'm using technical terms, but I'm going to try to make it so that you at least understand the gist of it. So this was basically a make work assignment. Get this kid out of our hair. He doesn't know what he's doing. Give him an assignment for the summer. I wrote this thing in about a week to 10 days, turned it into my manager, and we ran the tests, and it brought these mainframe systems to their knees because they were not designed to do this kind of large-scale arithmetic. And but I thought it was cool because we were generating really, large prime factorizations. We were finding really big prime numbers that, not new ones, but big for us. And they were impressed with this to the point where they ended up trading with the company that made the mainframe. I'm trying not to use brands and things like that, but the company that made the mainframe, they traded this software for them to use in one of their benchmark facilities for us to get, for Michigan Bell, Ameritech, to get something back from them. And the person who was my manager at the time, or I guess the lead on that team at the time, kind of took me under his wing. In fact, he's your godparent. And taught me a whole bunch of stuff. And within a few months, I was working on operating systems and compilers and all kinds of stuff like that. For the people who are not technical, that's like the guts of what makes your computer work. And it's not something to be taken lightly, but I had enough of the theoretical underpinnings from my own study and my own reading to be able to do that. And I fully credit my mathematical training for all of that, because it gave me a way of thinking about things that was different than traditional education, traditional computer science education. And I believe made it so that I could learn those things a lot faster. But that was probably the closest I had come at that point to what I would call applied mathematics, is that kind of work. So I rambled for a bit. Sorry.
No, that's good. Okay, so there's a lot to cover there. I'm trying to figure out where to start. I would actually like to cover a couple of terms. I think one of the things that is going to help people follow the thread of this discussion is to just lay out some terms in a way that is salient for people.
Sure.
So first of all, you mentioned being a mathematician who didn't have a strong hold on arithmetic. Can you sort of define what's the difference between arithmetic and mathematics as a whole? Because I think a lot of people, especially in current education system, that's interchangeable for them.
Sure. Yeah. It is for a lot of people. So arithmetic is adding, subtracting, multiplying, dividing. I mean, it's the computation part of it, right? And that actually makes me laugh a little bit too, because many people forget the basics of arithmetic, especially when they rely on computers quite a bit. I had an incident where someone was calculating a budget and using a little pocket calculator, and this person switched over to using a phone calculator and was getting different results. And she was utterly confused about, why am I getting different results? This doesn't make any sense. And I picked up the pocket calculator as a cheap little grocery store calculator, and I started doing something, and I said, oh, this one doesn't respect algebraic order. And she said, what? I said, well, the order of operations, multiply, divide, add, subtract, in that order. And she looked at me like I was from space, and she said, I don't understand what you mean. I said, well, you have to do your multiplications first. Then, your multiplications, divisions first, then your additions and subtractions. And she said, I never knew that. I said, you had to know it at some point, because you're probably taught that in grade school, but shouldn't remember that. So that's this little side story, but that's arithmetic. Mathematics is a broader topic. Mathematics studies so much. There are abstract forms of mathematics where you're very rarely using numbers. You're using symbols quite a bit. So for example, algebra is not just arithmetic, but it's things like equations and functions. Geometry is a form of mathematics where you're studying figures and shapes. Topology is a form of mathematics where you're studying characteristics, essentially, of we'll say shapes. I don't want to get too technical on things, but and how they change and how they're invariant over with different kinds of things that happen to them. So like take a balloon and inflate it. What are the characteristics of the balloon that stay the same? And what are the characteristics that are different? Take something like, here's one of my favorites. Imagine you had a donut or a bagel, and it was just super elastic, made out of putty, but you could just deform it and shape it, but you couldn't break it. You can't tear it apart, but you could pull it, and then you could make a little handle, and then you could kind of like make an indentation in it, make the indentation bigger. And I really wish, I know for the people who are going to just be listening to this, it won't make sense. And we could draw a picture for the other people, but you could actually turn that donut into a coffee cup by just, imagine yourself, changing and forming and reshaping it. That's all mathematics behind that. And there's a mathematics that studies, okay, under those types of what we call transformations, what is invariant? What doesn't change about that donut? How is it still a donut and a coffee cup at the same time? And what does change? What are the variant pieces? And I could go on. I mean, there's so many branches of mathematics. You use computers, you use networks. Networks come from graph theory. Graph theory is the study of these sort of ideas of points or nodes and relationships with other points or nodes. So if you've ever built those models where you have sticks and balls, and you put the sticks inside of balls, and you stick another ball on the end, and you make molecules and shapes and whatnot, that's graph theory. And there's a whole set of mathematics behind it. So that's all of the crazy cool stuff.
So sorry, I'm frantically taking notes.
Yep.
So I'm trying to formulate questions because, I mean, there's a lot to cover here.
Mm-hmm.
It seems like there's obviously something in common about those topics. I mean, you're covering the study of relationships and patterns and, the strength of relationships, but it's hard to pin down a definition of mathematics. Maybe another approach would be to talk more specifically about some of the interesting ideas in mathematics.
Yeah.
And, we had a discussion about, a little less than an hour ago, pre-show, about what would be the overarching goal of this conversation.
Mm-hmm.
And you mentioned something very specific. I don't know do you remember your specific wording? If not, I can repeat it to you.
I don't remember my exact wording, but yeah, go ahead.
Okay. So you in particular mentioned that other subjects in school are presented as joyous. When someone studies music, when someone studies art, when someone studies literature, those subjects are presented as joyous. You use the example of parents say, "Oh, I can't wait for you to take this music class because studying with you is going to be so interesting and fun, and it's going to be so cool to watch you blossom as you, I don't know, learn to play the trumpet." But it's very rare. It seems it's very rare that parents have that same enthusiasm for sparking joy in themselves and their children through the study of mathematics.
Sure.
So in my mind, that is one of the overarching goals of this conversation, is to show that you can have enthusiasm in that sense about this subject, and to see what that looks like. That, growing up with you as a dad, I think that was a constant switch along my life of running up against that pervasive attitude about mathematics coming from the world around me versus your attitude about it, and having to reconcile those.
Yeah. And I think there are a couple of themes there that that stick out. One, and we'll go with this one first, is that when it comes to things like music or art or literature, or those things that parents are going to be involved with helping their kids study, the parents are really enthusiastic about the things that they did well with, and oh, that's going to be so great. But I think there's actually there's a chain of things that happen, and I have an idea of kind of where it came from. But if a parent maybe didn't do so well with math, then they're gonna, oh my God, I hated this in school. Oh yeah, we're gonna have to find someone else to help you study this. Wow, yeah, I don't know. I don't remember how to do this. This is ridiculous. Why are they asking you to do this kind of stuff? And it's stupid. Just use a calculator, right? That's the kind of thing that happens so much. And my point of view is that as a parent, even if you don't get it, if you don't understand it, but your child has some even even spark of like a hope of understanding it, you should be enthusiastic. You should be supportive as much as possible. If you don't get it and you can't help, find someone who can, but stay positive about it, because your child might be a budding mathematician, might really be able to take this to the next level. And I think that's a pretty important part of it. The other part of it, though, is that, and this happens a lot, if I approach you with music or art, you're probably not going to ask me about what the practical applications are. Right? You're just going to enjoy them, because that's the idea behind them, is that they're enjoyment. Math is one of those things, it's a hybrid. It is both poetry and engineer. Math in its pure form is just amazingly beautiful. And it doesn't have to mean anything. And it doesn't have to have an application. But when it does have an application, that's when people change, where they say, oh, well, now that it's had an application, I get it, all of it should have an application. And that just can't be the case. That's not the case. Many things that we've studied that are abstract, pure mathematics, never see an application. And many, many more, like the Brian Greene quote, do actually lead. We look at those things and we say, wow, that's like imaginary numbers, for example, that's a weird one. Well, no one's ever going to use that. And a couple hundred years later, we are navigating in space by using just that. Like, we're using those concepts even at a level beyond. We're building all sorts of technology with computers and 3D graphics and virtual reality and things like that, using mathematics that 50, 60, 70 years ago, people would have said, oh, that's nice and abstract, but we're never going to do anything with it. But I don't really think that's the goal. The goal for me as a pure mathematician is to help kind of understand the structure and the beauty of it, and to continue to advance it, and to show other people that beauty and that joy. But for the practical side of it, I do think that there are some things that people can learn if they dig in a little bit deeper and open their minds to just, I would say, just a sliver of abstract thinking. So that's a pretty important part. And I'll kind of give the floor back to you, but I wanted to say sort of one more thing on that. And it's the I call it the shutoff switch. Like, when you start to talk to someone about mathematics and you use some, so I'm going to go mathematical on you for a minute here, and we'll see how many heads explode, how many eyes roll, or how many people just go, yeah, okay, I get it. But if I introduce to you a concept and I say, okay, we're going to let A equal the long side of a rectangle, and we're going to let B equal the short side of a rectangle. And so those are the sides of the rectangle, and I want you to compute the area of the rectangle. Now, I've worked with students, I've worked with tutoring people who say, okay, but like, what are the numbers? Like, what is this A and B thing that you're throwing at me? Like, just tell me how long it is. What's that? Well, it's A, that's the length. No, but that's not a number. Well, it is a number. It's just an abstract one. It's just a different letter. Numbers are really just letters, just the ones you're used to. But as soon as you start to introduce things like variables, oh my goodness, people just shut off. They just go, I don't get it now. Because that was like this tiny level of abstraction above the concrete where they normally live, where they can measure something with a tape measure. And I'm saying, all right, well, let's say you don't know the number, and we just put a letter in place for that. And we're going to just see what we can figure out from there. That shutoff switch is probably the biggest barrier. If you can get beyond that, then you can start to introduce people to mathematics that will just change their minds, just blow their minds, because it's so cool, it's so powerful, and I think it's beautiful.
Yeah, I think, and the way to explain that, in case anyone's mind did shut off when the letters came out, because I know that, I mean, you're right, that is a huge piece of why people shut off when the letters come out, unfortunately. the reason that that's important is you can have an abstract representation of the instructions of what to do in a certain scenario. I mean, this is the first use case for the abstraction. You can talk about what to do without knowing when you're going to have to do it or in what scenario. Computing the area of a rectangle, you don't have to know the numbers. You have to know you have to multiply one side by the other.
Right.
And you can put that in English or you can put that in math. Either way, it's an abstraction of essentially the instructions of what to do.
Yeah.
And in my mind, as I see it, once you get over that hump, then you can pull the field of view out a little bit more and see that you don't necessarily have to know the numbers to understand the relationships between things beyond just instructions for finding a practical application, right? You can use those abstractions at large to understand relationships between things in the universe. You can use those as principles upon which to we'll talk about mathematical games and things like that. You can use them to construct areas of mathematics that are far enough removed from practical application that it'll make your head spin. But then, just like you said, that's where imaginary numbers were 60 years ago. And now, because people did the pioneering work on the super abstract concept and, tried to understand something where they were that far up above solid ground in terms of practical application, now we have done so much with that we can use it without being blocked by that barrier of, well, we don't understand it.
Right.
So does that sort of make sense? That I'm trying to get out my understanding of what you were just saying.
It does. Yeah, it makes a lot of sense. And I think you uncovered one of the other barriers is the constant need for it to have a practical application.
Yeah.
Like the idea that, why do I need to do that? Well, you don't. It's kind of just because it's interesting and it's a different sort of point of view. So many people will immediately say, but I don't see a practical application for it. And my point is, don't try to. There might be some, but don't try to do that. And the other thing that I kind of, the analogy that comes to my mind is one of music, right? When I start to look at the sort of the structure of music, and I look at these symbols, right? The symbols in math are not the math. It's the arrangement of those. Just like in music, a given note is not the music, it's the arrangement of the notes. And writing that down in some notation is just a way to help us think about it. Having a notation that we can write down and think through abstract concepts in music, in mathematics, and whatever, that's really the key here. So the symbols aren't the math. It's how we arrange them and how we use them and how we move forward with them. So the example I gave earlier of the donut and morphing that into the coffee cup, it's like, well, yeah, that you don't really need to do that, and it doesn't really matter. But what happens is when you start to study those invariant properties, not just of that shape, but of other shapes, more powerful and complex mathematics emerge that allow you to do things like construction, allow you to do things like protein folding, allow you to do things like understanding advanced biochemistry and other kinds of things. There will be applications eventually for some of that, but if you go into it looking around every corner and looking for every single thing to have some practical use, you're going to miss the beauty of it. You're going to miss the cool and the fun part of it. Like, to me, even if that torus thing, the donut, it's called a torus in mathematics, the donut to coffee cup thing, it's just funny. It's just like, oh, well, it's invariant. It's the same thing mathematically, but the fact that, in a physical shape or form, you turned your donut into coffee. That's kind of just silly, but it's fun.
I like how when you were talking about how you experience math, and were curious and went and discovered things and looked into new ideas and tried to problem solve basically and just pursue your interest. That really corresponded to how I learned music and had my music education. So I like that you brought in music there, because it's the same way I felt when I would discover, oh, what's this thing, and bring it to my teacher and say, oh, we'll learn about that in the next theory class. Don't. And
Yep.
I kind of had a similar reaction from some of my teachers that were similarly not super supportive and just, oh, we'll get there. But there is, and going back to the kind of a connection there, like you mentioned, an analysis of music theory does the same thing. It gets to a higher level so you can abstractly think about things without having to practically do all of the little things. That like gets to a higher level so you can use fewer resources to compute music, basically.
Right.
I thought that was a really apt comparison.
Yeah, and I'm not a musician. I've tried to be at times, but I'm sure that there are terms where you can use a term that might be one or two words that is an extremely complex concept, but now it gives you a compact form for language and notation to be able to talk about that concept. And you don't expect that everyone will understand that. You expect that other musicians will, but at least I think as lay people, as non-musicians, those of us who are not musicians, we can appreciate it, and we understand the sort of the beauty and practicality of it in both cases. And I think that's kind of where I'm getting at with math. That notion of, okay, let's just dig a little deeper than what you've gone. Just make your brain hurt just a tiny, tiny bit, and the benefits are just amazing. That if you give yourself that extra percent of push, you are going to advance so far above the common person that it's just going to be amazing. There's actually a book that I read when I was in 9th grade, and it was my friend dad had this book. It's called The Education of T.C. Mitz. T.C. Mitz stands for the Celebrated Man in the Street. And it's about kind of that same idea of let's push you a little bit beyond. And I do have some, you mentioned mathematical games and ideas. I do actually have a couple of things that I wanted to push the audience with when we get to that.
I was going to jump into mathematical games next, so let's talk about that. What do you mean by mathematical game?
Well, okay, so before I get to the games, I'm going to talk about statistical thinking a little bit. But by mathematical games, I mean playing around with math just for the fun of it. So there's when I was much younger, I think I probably started reading Scientific American when I was in I want to say 4th or 5th grade, somewhere around there. I was reading Scientific American, and there's a guy named Martin Gardner who wrote the Mathematical Games column. And I grabbed one of his books. I probably have a few others around here, but I have one called Wheels, Life, and Other Mathematical Amusements. And the idea behind mathematical games is puzzles and games, logic games, graph games, all those types of things that are just sort of fun little things to play with, including things like, proving that tic-tac-toe is basically if you go first, you can always win, showing other types of games that can come up. He did all kinds of things, games with coins, games with cards, mathematical card tricks, all this kind of silly stuff. And I just ate it up. In fact, one of the games, so I guess I will go into this. No, I'm going to save this one. So I'm going to save one of the games that came up, or puzzles, I guess, more than games. But games and puzzles, you know, they're very similar idea. I'm going to save that for the next section, but I wanted to run this by the group. Okay, so I'm going to paraphrase this a little bit. And actually, I'm paraphrasing it for a specific reason. I'm not going to go into too much, but a guy named Kit Yates talked about this on Science Friday. And I remember it a little bit, but imagine your favorite food. Okay, and I'm sure, you know, I'm not much of a foodie, but I think a lot more people love food more than I do. So if you really love food, right? Imagine your favorite food, and maybe you can put this in the chat. Not what it is, but oh, you can put that too if you want. But if I told you, hey, there's a study that just came out that shows that there's this horrendous disease, won't name the disease, but some horrendous disease that you really don't want to get, and eating your favorite food increases your chance of getting that disease by 20%. How many of you would think a little bit about, maybe should I be eating as much of my favorite food? So if you think, you know, maybe, like, just put a little yes in the chat if you think, yeah, I would think twice about maybe eating my favorite food, and maybe drop a no in there if, like, it wouldn't deter you at all. Okay, so I'm seeing kind of what I thought I would see. And there's at least one person who said, no, hey, I'm not giving up, you know, chocolate or whatever it is. No way. But a lot of people, yeah, that sounds 20%. Holy crap. But it's going to increase your chances of getting this disease, this horrendous disease, by 20%. Yeah, there's a lot of those. Okay. Okay. And that's kind of what I expected. The problem is we're dealing with something that is known as statistics. And it's the worst of the three types of lies. There are lies, damned lies, and statistics. And statistics is the worst of the three types of lies. Now I reveal to you that the 20%, and this is actually how this was phrased in a news article about, well, they talked about it as eating bacon sandwiches over in some newspaper in the UK. Okay, so now the statistics come out, and we did the study, and let's say of 100 people who did not eat bacon sandwiches, 5% of them got this disease, colorectal cancer. 5% who did not eat bacon sandwiches. But of the people who ate bacon sandwiches every single day, 6% of them got colorectal cancer. That is a 20% increase. 5% to 6% is a 20% increase. But now you say, okay, wait a minute, but 6%, I'm not giving up my favorite food for that. That's kind of ridiculous. Because now you're looking at the numbers a different way. I lied to you with statistics. I didn't lie, the statistic was correct, but the way you interpret it is really based on the numbers that I give you. I didn't give you all of the information, all of the evidence. And now that you have all of the evidence, all of the information, you can make a more informed decision. So now, knowing that, yeah, and someone pointed out, the statistics is not the problem. It's how we interpret the statistics. The statistic was correct, but we needed more information. So now, knowing that, how many of you would give up your favorite food for a 5% to 6% change? You probably wouldn't. So that's kind of one of the things I wanted to just sort of play with the audience on, is that notion of statistics. Okay, so hopefully that was sort of interesting. And now getting into the games thing, one of the puzzles that came up, I think this one was a little bit later, after I had kind of after I was in school and I'd been working for a while. I actually saw this puzzle when I was younger, but it came back up later in life. It's called the 8 Queens problem. Now, probably most of you have heard of chess. Many of you have played chess, but not everybody has played chess. But if you know, in chess, there is a piece called the queen. The queen can move along horizontal, vertical, or diagonal any number of squares as long as it's not blocked by one of its own pieces. And if it encounters a piece from another player, it can take that piece off the board. Okay, is that a pretty simple explanation so far? Good. So that's the moves of the queen. Now imagine for a moment, instead of just the normal chess pieces, we clear off the chessboard. And by the way, the chessboard is 8 squares wide by 8 squares high. So 8 by 8, 64 total squares. Imagine now that we take 8 queens and we put them all on the chessboard at once. But we want them to be arranged in a way that they're in different rows, different columns, and different diagonals. In other words, if I stuck them all on the top row of the chessboard, they would all be attacking each other. Let's assume that the color of the piece doesn't matter, like, you know, black or white piece doesn't matter. They're all different colors, rainbow queens, right? So they're all different colors. They're all attacking, you know, their adjacent queens. So I'm going to start moving them around in a way that, hey, they're not attacking each other at all. And the question is there an arrangement of that works? And if so, how many different arrangements are there? So that's a kind of an interesting one, right? And you could sit there at a chessboard, you know, all night long, moving pieces around. I've known people who've done this, moving pieces around, trying to figure out how to get them arranged that way. So a friend of mine who was studying computer science came to me and said, hey, you know, we're doing this cool thing with this thing called 8 queens problem. You can actually generalize it to more than 8 queens, like if you have a bigger, like a 9 by 9 board or 10 by 10, and we're going to throw in a letter here, n queens, so where n is any number. So generalize it. He said, oh, yeah, we're doing this 8 queens thing, and they were doing this using some computer sciencey stuff called tree searching. Basically, it's a matter of taking a board, changing the board a little bit, and building out like a whole array or network of these changes to the board until you hit one of these potential solutions, or you hit a solution, and then you can backtrack and then start changing it in a different way and go like just this massive set of things, but essentially generating all of the potential board positions. And he said, hey, I've been working on this, and we run it on this mainframe, and we you know, like run it for, I don't know, 20 minutes, 25 minutes, whatever, and it comes up with a solution. It's really cool. You should try it. And so I didn't have access to his mainframe, this big crazy computer, but I had a little computer at my desk at work that ran a language called Pascal, a little tiny, you know, language that runs locally, and I had a computer at home that would run Pascal. So I decided I'd give it a try. And mathematical thinking kind of came into play again when I realized, hey, like thinking about this board in a different way, I could cut down the amount of searching that I have to do for a solution. And I'm sorry if this is getting way too technical for people. Tell me if it is. But now, using your imagination again, let's go back to those 8 queens on the board, on the chessboard. And on the bottom row, we're going to number everything from, say, 1 to 8. Actually, usually in math and computers, we do 0 to 7. But we'll just say 1 through 8 on, from left to right, and from the lower left corner up to the top. So we have rows 1 through 8 and columns 1 through 8. And on that bottom row, I just want you to, in that square, write the number that corresponds to the row that the queen is in. So if she's in the top row, you're going to write an 8. If the queen is below that, you're going to write a 7. If it's all the way down at the bottom, you're going to write a 1 in that first lower left corner. And then work your way across the right. And for the next queen, just write the number of the row that she's in, and so on, all the way down to the end, right? So now that bottom row just has some numbers in it that represent the row that the queen is in. Now, if you think about that for a moment, you could actually just eliminate the top part of the board. All you need to look at representation-wise is that bottom row. It tells you everything you need to know, because the column that the queen is in is just the column that you're looking at, column 1, 2, 3 through 8. The row that the queen is in is the number that you wrote down there. Okay, so now we've got a starting point. Now I just want you to write the numbers 1 through 8 in there. And now if you're thinking ahead and you're thinking abstractly, you're going to immediately realize, oh, but that's silly, because that means the queens are in a diagonal and they're all kind of attacking each other. But what I've done is I've eliminated, if all you ever do is write 1 through 8 in there in some different, we'll call it it's called a permutation, but basically that means swapping the numbers around a bunch, but in never repeating one of those numbers 1 through 8 down in that bottom row. But if I take that and I start out with 1 through 8, and that basically, like I said, it's diagonal, and I start permuting that, just moving the numbers around, then I get a different arrangement. Now I can actually systematically swap those numbers. Swap the first and the second, the first and the third, the first and the fourth, the first and the fifth, and so on. And then start in the second and third, second, fourth, second and fifth. And like I just progress through this, systematically swapping those numbers. And so that's what I had my program do. Now the program has eliminated searching a whole bunch of stuff that it never even has to think about. And by searching just those permutations, we actually have cool algorithms for really quickly. And this is an abstract part of, like, oh, so we go back to our pure math. Someone came up with a mechanism for generating permutations, didn't think, oh, I don't care if it's ever applied to anything. I apply it to this. Now I can really quickly generate all of these permutations. And I just have to have a really simple set of rules for checking to see if any of the queens are attacking each other. I won't go into all of the details about that. You can kind of work that out, or we can talk about it later. But what that did for me was now I could generate all the permutations of the 8 queens in sub-second time and test to see if they were potential solutions, write out those solutions and count them. So what I did in sub-second time on a PC was to generate all of the solutions for the 8 queens problem, which my friend then took back to his computer science teacher and said, oh my goodness, look at what my coworker did. It took us 20 minutes on a mainframe to generate one solution. Power of mathematics here. Representation matters. How you think about things abstractly can lead to solutions that are far above what you might do if you only think about a problem in one way. And so by thinking about problems in different ways, different representations, you can solve problems in just really amazing ways. So you know, kind of that was a real big, like, I think one of the cool moments for me of being able to apply mathematics in the sort of the quote real world, but in just a really, really powerful way.
I'm definitely going to have to listen back to that, or actually I'll probably just ask you.
Oh, Chase, you're muted.
We're
not hearing.
Can you hear me?
I hear you.
Oh, okay. I wonder if your headphones.
My volume go.
Slight technical problem.
There we go.
Okay, cool.
Gotcha.
So I was going to say, I think in the details of the problem, you lost me a little bit. I'm going to have to ping you about that later.
Yeah, push that a little.
That's pushing my limits of internal computational power, and I think part of that is because I'm a kinesthetic and visual learner. I don't do a lot linguistically, despite being on a podcast.
Yeah.
And having my own podcast. I think that for problems like that, I like being able to write it out myself, and that's the best way for me to learn it.
Sure.
But I think the broader point I take, which is, well, there are several. First of all, that is an application of previously studied abstract concepts that, had someone not done the work to explore those things, you would have not had the groundwork laid for you to just think through in that way. Like you said, someone laid the groundwork for permutation calculation and figuring out how to do that, which laid the groundwork for you to solve this solve this problem in a novel way. The other thing that I take from that is essentially that something that starts out as an interesting sort of entertainment value problem actually has potential real world applications, in that you came up with, for a game, a search algorithm that now is in the, I guess, the body of knowledge that is the world of mathematics, that should some engineering problem come along where you're starting to see similar patterns to the problems of the 8 queens problem, you can potentially apply that algorithm to a real world application. I know that we're still stuck in, the fact that real world applications are where we're grounding ourselves.
Yeah, and that's fine. That helps people. Yeah,
right. That's what I was just going to say. I think that that's a really important step for people, and I think that just convincing people to let go of the ground beneath their feet and live in the abstract world is beyond the scope of what I think we'll do in this podcast.
Sure.
In the next half hour or so.
Yep. Yeah, I agree, and that's one of the reasons I like mathematical games, is that they have enough of that concrete, real worldish feel, like there's an application, but they expose you to the abstract in a kind of an underhanded way, right? Because you're playing, and when I can expose you to that abstract in a way that you're playing, it helps you to practice that kind of lateral thinking, which I used to call sideways thinking, but that sort of lateral thinking where you're going to learn some abstract concepts that you can apply later, even if you can't name them, even if you can't put your finger on exactly what they are. My push to the group and to most people is to try, like I said, just give yourself that little tiny boost of making your brain hurt for a little while to push through an abstract concept. And I do have, actually, I have, so there was one other that I wanted to talk about, but I was going to leave the group with a kind of interesting set of puzzles too. Do we still have time for that? I know we're right at the 10 o'clock time.
Yeah. So I would say, do you want to finish out with the last puzzle or set of puzzles?
Yep.
Because I still have a couple more things.
Oh, okay, sure.
So I think there's a third point to make in that. So this is actually, I'll tell it in a different way. About 3 years ago, I was working on a computer programming problem that it was an audio programming problem that had to do with spatializing sound in an environment and essentially redirecting around. I won't get into too many of the details, but the point is, it was an audio programming setting. And I specifically remember talking to you about the way that math was taught and the fact that I got really lucky solving this problem because I paid attention, but the only reason that I had access to the resources I had access to is because I understood that there was some importance even if I didn't get it. So here's what happened. I was doing this audio programming, I was trying to solve this audio programming problem, and I came across a geometric form that I had seen before, specifically conic sections. There's conic sections, for people who don't know. Essentially, you can think of a cone, like a circular base that moves up to a point in 3D. And now take a slice of that at whatever angle you want. You can make a slice horizontally and it'll become a circle. You can tilt that slice and it's an oval. You can tilt the slice until one end is off one side of the cone, and now you've got a parabola. you can do all sorts of transformations of that slice and get different shapes. So those shapes are called conic sections. And we did a whole unit in geometry on conic sections. And the major complaint among me and my classmates was, why the heck are we doing this? This is fully useless. As high school students, we do not care about conic sections. Why are we doing this? We're being taught to memorize this. And so the only reason I think I picked it up, like I said, I got lucky that I thought it was interesting. But it turned out to have an application in the audio programming problem I was trying to solve. And I specifically said to you, wow, if things were taught in this way, where you're introduced to a concept, you are led through it in a way where you have a lasting impression of it, you have a lasting understanding that it's out there, but you don't need to, you don't need it drilled into you. This would open mathematics up to a whole bunch of people, because my actual process for using the conic section algorithms had nothing to do with the fact that I had memorized them in high school, and everything to do with the fact that I understood that they existed in the first place. Because you know what I did? I just went on Wikipedia and looked up conic section algorithms, right? And I looked through a bunch of reference material for, oh, here's how you use, this particular shape that's a conic section algorithm. And I easily could have gained that knowledge with 10% of the headache, because 90% of the headache was memorizing it, trying to do it over and over and over, studying for the test, and then, knowing that I was going to forget about 90% of it right afterward.
Sure.
So bringing us back to that original question that I had talked about, or that you had really talked about prior to us starting our recording, of bringing the joy into the subject. I wonder what you think the approach should be, or what your approach is for trying to spark that joy in people in a way that, even if they don't end up lifelong mathematicians, they've got that reference, like I had for conic sections, for a wider array of things that could apply to them, or just could be interesting. They could find fun and engaging.
Yeah, and I think a lot of that is the idea of mathematical games, of using math to solve puzzles, riddles, mysteries. I think, for me, putting that fun into it, it's kind of like it's a practical application that you can use mathematics for, but it's not a super serious one. So, like if you need to calculate how much paint to paint your house with, it's tedious, it's important, but it's not much fun. On the other hand, if you're playing around with some little game or puzzle that's sort of interesting, coding a word puzzle into a matrix and looking at how things intersect in the matrix to create a truth table, whoa, and then at the end you have a solution that's logical and consistent and clear. Like, that's pretty cool to be able to do that. Or, and I guess in some cases, on the non-game side, understanding things, kind of like the bacon sandwich thing, but there are others. I encourage people to look up things like Bayes' theorem, and there's some good explanations. 3 Blue, 1 Brown on YouTube has a really good explanation of that kind of talks about it. But this, like, learning to think just a little bit more logically and clearly about things that are presented to you in everyday life, and to question when someone gives you a number or a statistic that just sort of, makes sense, seems reasonable, but ask yourself, are you seeing all of the evidence? Are you seeing all the numbers? And is it really making sense to you? So to me, that's kind of how you can put some of the joy into it and some of the fun into it. One of the best, I think, contemporary examples of this is, and it's ridiculous, but it's the TV show Numbers. Because Numbers is a crime drama where the lead character two leads. One is a brother who's in the FBI, but the other lead is a professor of applied mathematics who uses math to solve crimes. And I've heard people say, watch the show and go, oh, that was kind of, fun, but it's kind of ridiculous because there's no way. And it turns out that almost every episode is based on an actual case that was actually solved using the actual math in the show. There's even a book that kind of goes through that, and there's a website that talks about the mathematics of numbers, of the TV show Numbers. And that's fun. Like, yeah, there's stuff in there that you're never going to understand, but it's just kind of cool to be able to see stuff like that where the mathematician is the hero. So I would encourage kids with stuff like that. I would think, yeah, like I said, games and fun with it and just playing with it. If you play with something, it's not so scary and dangerous anymore.
Have you seen people's kind of brains change with this type of practice, doing these type of puzzles? For example, studying, philosophy and just more abstract thinking in general, I feel like my brain has changed in how I look at and assess just basic problems, or even things I wouldn't have assessed as problems to be solved, but now do. Do you see that as a consistent thing, or in yourself and also others that you've seen study math?
I wish it were more consistent than it is. I see it with a lot of the students. I've tutored a lot of people over the years, and I occasionally see people who came in with they were sort of math haters and have left mathematicians. People who have gone on to do things like data science, people who have gone on to do other things that are related to mathematics. A friend who became an electrical engineer, and even recently I ran across a young lady who lives in Germany now. She's got a child, and she was saying that my tutoring helped her not only to pass math, but to love math and to be able to teach math to her children. And she said, well, there's things that I think about now that I think about in a different way than I ever would have until you're tutoring. And she was a teenager when I was tutoring her. I was a teenager too, but think about, it doesn't matter what stage of life you're in. I've tutored people who were in their 50s in mathematics and made a change, made a dent. So I see it, but I don't see it as often as I'd like, because for many people it's about, I just want to get through the test. I really don't want to learn it, but I'm failing, so I need a tutor. So help me to get enough mnemonics, enough learning aids that I can pass the test. And that's really their goal. And when you have that goal, that's all you're going to get. When you have a goal that is push yourself and learn something and push your mind, you can change your brain into something better than it was before.
Yeah, absolutely. And I think part of the burden of switching our mindset in general around mathematics lies on systemic change in education.
Yeah.
I think that, having gone through both an amazing school system that focused on teaching things the right way, and experiencing a school system that I think taught things the wrong way in terms of math.
Mm-hmm.
I mean, that makes such a huge difference. Just the expectations on the student and the environment that the student is in. Are you asked to study for a test, or are you asked to improve your understanding?
Yep.
So,
big difference. Yeah.
Do you have any favorite math? Like what's the stuff that if you're in a math mood, you reach for, that's, your sparks the most joy for you? Favorite equation, maybe.
Okay. So the things that I would say there are probably three things that I reach for most. number theory, group theory, and graph theory.
Definitions, please.
So yeah, number theory, really the study of the integers, how things, like prime numbers and all that kind of fun stuff works. Group theory is a different, how do I describe it? It's more like the study of well, symmetries, asymmetries. Group theory is a kind of a weird one. Imagine, well, let me think of a good example. Okay, imagine that you have, say, a cube sitting in front of you, and there are some operations that you can perform on that cube, like a die, the singular of dice. And there are operations that you can perform, like rotate it to the right once, rotate it to the left once, rotate it forward or backward, spin it on its axis. Those are some operations. And group theory kind of studies that in a way more abstract way. This is like a super simple, concrete example. But if you wrote down those operations and then you did some things like, oh, well, rotating to the right once is the same, so we'll call that, R1, is the same as rotating to the left 3 times, 1, 2, 3, or whatever. So R1 equals L3. And you're like, oh, okay, so these are operations and there's some equivalencies. And you can actually start building up a whole set of arithmetic, like on these operations of what does it mean to combine rotation with left and right with rotation back and forth with rotation about the axis. And basically build up a little tiny bit of math just based on that cube. Kind of a silly, simple example, but when you generalize it into structures that might be a lot bigger, so higher, we call higher order groups, basically, or even structures that are maybe infinite, although that's a different thing entirely. But you can do a whole bunch of things with group theory, and that's not the only thing in there. There are studies of understanding these group structures and how they can map into other group structures that may appear different, but have some similarities. So transforming from one to the other and maybe even going back. Sometimes it goes one way, sometimes it goes the other, sometimes it goes both. But that's what that is. Graph theory is really a study, like I said, of this abstract idea of a graph, a way to picture a graph, which when we do it in higher level mathematics is mostly symbols, but a way to picture it is just write a bunch of dots on a page and then start connecting those dots with lines. And you can find that you have a bunch of different ways that you can interconnect the dots partially or fully, and that constitutes what's called a graph. That's just, again, a really simple way. That's not like the only thing, but that's a simple way to picture it. Those are the things that I really reach for. I do find myself playing with number theory a lot. I love things like, I think I mentioned this before, perfect numbers. The idea of a perfect number is you can find all the divisors. So if you look at a number, my favorite one is 6. The divisors, the proper divisors of 6 are 1, 2, and 3. And if you sum those up, 1 plus 2 plus 3, you get 6 again. And there are some other perfect numbers like that as well. The reason I like 6 is because it's also the product of its proper divisors, 1 times 2 times 3. Find me another one of those. So that, I reach for stuff like that. Favorite equation is something called Euler's identity. It's pretty technical. Brian Greene in something called Your Daily Equation does a really great example of deriving it. What's amazing is that he starts with this notion of in calculus that is a way of approximating a function. Then he throws in compound interest, and then he throws in like some trigonometry, basically, sines and cosines. And he shows some equivalencies among these things and then just mushes them all together. He comes out with this equation that is probably the most beautiful equation in all of mathematics. I'll say it. I'm not expecting everyone to get it, but e to the pi I, and then back, that pi I is the exponent of e, then plus 1 equals 0. Silly, I know, but it has in it multiplication, exponentiation, the root of natural logarithms, fundamental constants like pi. It has imaginary numbers in it. It has the additive identity and the multiplicative identity, so 0 and 1, and it has addition in it, and it has equality in it, and it's like all the stuff that forms math in one equation. And it's kind of silly, but it is my favorite equation. So I have a favorite number and a favorite equation. I don't have a favorite color.
That's fair.
Yeah.
One of the things when you mentioned number theory, just real quick, I think this is an interesting way that an understanding of mathematics interacts with an understanding of the universe. Are you familiar with Galileo's odd number rule?
Oh yeah.
So when I first heard about that, and that was within the last couple of weeks,
Mhm.
that completely blew my mind. And
Yeah.
and I think the funny thing is, so maybe we should define it. Do you want to define what that is before we go
No,
too far?
well, so I think the best explanation that I have seen is there's again, back to YouTube. I think it was it Vsauce
Yeah.
that did
Mhm.
a definition or an explanation of it, but it's let me think if I can think of a good way to describe it.
If you want, I can describe it.
Sure, go ahead.
Okay, so for any uniformly accelerating object, think of something falling. It can be falling straight down. It can be falling on a slope. It can be falling on a slope of any angle. It follows this rule where, let's say the time in seconds, for every time that's elapsed in seconds, let's say it moves a certain distance in 1 second. The next second, it will have moved an odd number multiple of that distance forever.
Mm-hmm.
As long as it's uniformly accelerating. I believe that's how it works. So something can be falling, and in the first second, it will move 9.8 meters. And then in the next second, it will move 3 times. It will have the total distance. Is it the total distance traveled?
It's the total distance. So if you sum the intervals,
That's right. So the total distance traveled is 3 times that. And then in the next second, the total distance is 5 times that. And then 7 times. It hits all the odd numbers every time. Doesn't matter if it's on a slope. Doesn't matter what the actual acceleration is. If it's uniform acceleration, it will be in those odd numbers. That's just a true statement about the way acceleration works. And, it's funny that that's so amazing, because when you dig deeper into it, it couldn't be any other way. So a lot of people would see that and go, wow, that's a message from the universe. That's the universe speaking to us. I think that's what Michael Stevens said in the Vsauce video. He asked the question, is this the universe speaking to us? And then just goes on to show essentially the proof for it. That's one of my favorite sort of interesting math ideas.
That one's definitely good. I recommend that video too, because it's funny, as well as getting a lot of the math stuff. What's funny is that I showed it to my mother, who's not really a mathematician. She watched the thing from end to end and started asking questions about it to the screen. Like, well, wait a minute, what if this happens? Hold on. So that was pretty cool. Yeah, it's definitely a good one.
Alex, do you have any favorite math stuff? I'm just curious.
Yeah, so I was rummaging around through my books, and I can't find it, but I have a Monty Hall problem and other math problems. Yep. And I don't think I've been able to solve a single one of them. I really I find them fascinating, but I'm not sure if there's some conceptual limitation I have around doing it. For example, I feel like there's things in math. There's a very specific, I think this applies to lots of different areas of learning, but I noticed it the most with math was that it was like I didn't realize I could do certain things, until because it would just click, I could understand how to do certain types of equations. And it was just trying to figure out how to make it click in my mind. And then I understood it. And there's a lot of these problems when I go through and try to figure them out. I feel like the missing thing isn't kind of, like you said, a computational or arithmetic issue I'm having. It's a kind of a limitation around what I think the functions I'm able to use are. It's like a lack of understanding the expanse of tools in mathematics. So that's something I feel like is like a gap in my knowledge that I really want to fill because it's frustrating. I see it, I feel like I understand kind of where I'm going, but I don't have the tools. Is there any specific place you would recommend, for example, I could start that would either kind of cultivate that curiosity or just learn any mathematical problems that you feel like have principles that I could learn from and apply to other types of problem solving?
Wow. The places I would look, it depends on how you learn. So I mentioned 3 Blue, 1 Brown. That's a really great YouTube channel for math and learning and playing with math. It won't teach you everything, but it introduces you to concepts that you can then kind of go and study further. If you want to go from first principles, then something like the Khan Academy is really good because you're going to start out, sort of page 1 and work your way through. Finding a tutor, finding someone to talk to who understands what's there helps a lot. And I'm going to give, so to the world now, to the world, I'm going to give you my secret sauce that I use whenever I'm tutoring and someone is stuck. I ask them 2 questions and I say, write this down. And I think you hit on it, not knowing like, what are my tools? I say, write down what you know. Okay, so then they'll write down, okay, well, X equals this, Y equals that, blah, blah, blah. And if they miss something, I'll say, well, look at the other thing. Oh, it says here that, X is half of Z or, whatever. Okay, I forgot to write that. So that's the what you know. Now, what do you know about what you know? Oh, well, I know that I can take a derivative of a function. I can integrate a function. I have an angle here. Oh, I can like do sines and cosines and tangents. And like there's all the stuff that you know that you can do with the things you know, all the operations that you can perform, what I know about what I know. I know this number is odd, this number is prime. Those are the things, the metadata. And eventually when they start listing that stuff out, they'll hit one and just go, oh, wait a minute. If I know this thing and I have all these other things, oh, I can start combining and solving, and like eventually they hit it. And almost every time, I don't help them solve the problem. I help them solve the meta problem. I help them with, what do you know? What do you know about that? And it's just like floodgates open. And I think the difference in that versus the approach of me telling you what steps to take, okay, now take the derivative, okay, now add, is that you're doing something mechanical, which you can learn to do, but you have no idea why you're doing it. You don't have a concept in your brain's language that makes sense. By me just kind of asking you the questions that skirt around that, if you're a visual thinker, you're going to draw a picture. If you're a linguistic thinker, you're going to talk it out. If you're a kinesthetic thinker, you're going to get up and move it around, and you're going to do whatever it is that you need to do to make it work, as opposed to me telling you how I would do it. So when you're studying this stuff, do the same thing. Everybody can do this now. You can just ask yourself, okay, what do I know? And what do I know about what I know? And that will help you solve a problem. And I apply that to everything, any kind of problem that I'm solving, not just math problems, but any kind of problem that I'm solving, plumbing problem, electricity problem. What am I going to have for dinner? I don't know. Maybe not that. Who do I know and who cooks better than I do? That's the, but so that's kind of what I would look for. And of course, I'm always game to chat with people about math, and if there's an area that you want to explore, I'm always game to kind of chat about those things.
Yeah, that's great. I think that's explains a lot how when you described it as like a meta problem, because it's a kind of a problem with the conceptual framework of how I'm thinking about it, not actually any specifics of it. Also, I think, could you touch a little bit more on the differences when learning math in, for example, the kinesthetic or linguistic type of learners? Because, for example, when Chase mentioned that how you described it kind of lost him at some point, I would consider Chase much better than me at math, but how you explained it made total sense to me. Like, I was along for the ride, and I feel like it made a lot of sense. What are those differences in learning, and how do you kind of assess?
Sometimes it's a little bit of just watching people and what they naturally do to solve problems, and just sort of letting them do it. When I was 17 years old, so I was I guess freshman in college, because like I said, I started young. But when I was about 17, I got a summer job teaching in a summer school in New Jersey for gifted and talented children. And some of the kids in my class were teaching a programming language called Logo. So I was doing math and programming. And Logo, there's this little thing on the screen, they call it the turtle. And you give it commands like go forward, turn right 90 degrees, go forward. And it draws lines and stuff on the screen. So, we're trying to draw a box. And that was really easy. Like most people get that right away. It's like, go forward 10 steps, turn right 90 degrees, go forward 10 steps, turn right 90 degrees. Like you can visualize that. There are some kids who have to stand up and walk it out, and they have to do that. And I would say, okay, it's time for you to play turtle, because the turtle is on the screen, you're playing turtle, get up and walk it out. And they would get up and they would walk it out, and they'd draw the thing on the screen. So they'd figure that out that way. And there are other kids who would just draw a picture on a piece of paper, that was good enough, or they would kind of, in their head, just look back at the sky for a moment, visualize it in their heads, okay, I got it. And then there are other people who would just say it out loud, and they would be able to solve the problem. What's really funny about that is I had parents come in, and that was one of the first things that we would show. We'd show some more advanced stuff later. But I had a group of parents come in, and one of the dads saw the first thing was, oh, we're going to draw a square with the turtle. And he said, man, that's all you guys learn in here? And I said, no, we got some really advanced stuff to show you first. But why don't we switch? Kids, get up and let your parents sit down at the screen. And the parents all know the commands now, forward, right. I said to the parents, okay, draw me a triangle on the screen. Well, that should be easy. And they go forward, 10 steps or whatever. And then they give the command to turn the turtle right. How many degrees do you think they turn to draw a triangle?
25, they probably do, right?
Well, most of them would go, okay, I remember this. Sum of the angles of the triangle, that's 180. So divided by 3, and they would turn right 60 degrees. And then they go forward. And then they look at the screen and go, oh, wait a minute. That's not enough. Because if they turn another 60 degrees, those lines aren't going to connect. And then they would scratch their heads and kick back, and then you get the 5 or 6 year old kid who goes, no, daddy, it's, let me show you. And the kid shows them that it's that outer angle that you care about, not the inner angle, right? So you really wanted that thing to go 120 degrees so that it came all the way back around and was pointed in the right direction, so that that inner angle was now the 60 degrees that they were looking for. And that was sort of the point at which they go, oh, wow, okay, My 5-year-old figured that out. Okay, now we're on to something. Then we would go on and we would show how the 5-year-old wrote a program that could draw any polygon, any regular polygon of any size on the screen. And then how they composited that program to draw a house and a car and whatever else it might be. And meanwhile, the older kids were writing programs that would parse sentences and have conversations with you, and all this really great stuff. But again, they all thought differently about how to solve those problems, and it was just, you just have to backtrack and go, okay, what are the ways that these people, how do they think? How do these kids think? So that was kind of the key.
That's awesome. So I want to make sure that we're being mindful of the time. Do you want to throw out your last challenge to the audience before we move to the off-topic and questions?
Sure. So my last challenge, and we didn't talk about my favorite mathematician. It's Carl Friedrich Gauss. And there are all kinds of stories about this problem that I'm going to give you, ranging from, so Gauss was like 5 years old when he solved it, and he was in school, and there's like the anecdote of, oh, he was being naughty, so the teacher had him do this after class, or the teacher just wanted to make work for the whole class. But basically, Gauss was told, add up the numbers between 1 and 100. So 1 plus 2 plus 3 plus 4 plus 5, all the way up to 100. And so the challenge is this: don't do it on a calculator, right? Don't go looking up stuff online to figure out a formula for it. Just do it on paper. But the hint that I will give you is that if you write down the numbers 1 plus 2 plus 3 sort of in a line, you don't have to write all 100. You can like do the little 3 dots thing, and then at the end write plus 100. And then underneath that, write backwards, 100 plus 99 plus 98, and then all the way down to 1 is going to be the last one. And then you add up those 2 lines. So that's my hint. You add up those 2 lines. You don't have to write all the numbers to see the pattern. But if you add those 2 lines up, you're going to get a really easy way to compute the sum. But it's going to be twice what you actually needed, because it's going to be 2 lines of 1 to 100, not just 1 line. So figure that part out. And then you will have figured out how to sum up the numbers from 1 to 100 with a simple calculation that doesn't require you to add them all. Now, the tricky part that I'll leave you with is make that more general. So in other words, 1 through n, not just 1 through 100, where n can be any number. I could say 1 through 50, 1 through 30, 1 through 1,000. I'm going to give you that n sometime later. You generalize it, you figure it out. So that's part 1. Part 2. This one, you might say right away, oh, that's not related, but it is. So get a bunch of pennies, if you have pennies laying around the house. Stick one on the table, and then put some pennies around that so that they're all touching each other. You'll find that in the first, we'll call it layer, there's only 1 penny. The second layer, there's 6 pennies, right? So if they're all touching each other, that's how many you can pack in together. And there's some technical mathematical terms for what you're doing, but who cares? Then take another layer and stack those all around so that they're all touching, and count how many you have in that layer. And then do maybe a couple more, and write those numbers down and see what it looks like. So you're going to be able to write down, so what you know is how many pennies are on each layer. And then for any given layer, how many total pennies there are in that layer on back, right? So starting at 1, 2, if 1, and you add the second layer, there's 1 and 1 in layer 1, 6 in layer 2, that's a total of 7. And you add, say, 12 more, and then so that's a total of 19 or whatever. So figure out how many in each layer and the sum of each layer. See if you can come up with a formula that will tell you at any given layer how many they're going to be and what the total will be. The work that you did in that last problem will help you to figure out the second problem. But you have to think a little more abstractly than you might be used to. So that's my challenge problem, is pretty simple arithmetic, but challenging enough that if you're not, quote, good at math, it'll be harder for you. And if you are good at math, it's just fun because it's really easy for people who are mathematicians.
Nice.
So, have you ever had a challenge problem from the Switch before?
Never. This is awesome. Okay, cool. Any other topics that you want to hit before we do the off topic?
Nope, I think that's it. I mean, I had a lot of stuff that I could talk about. Obviously, I could probably talk about this more than I thought I could. And well, I'll probably leave you with a few links so that people who watch or listen to the show can go find some of the fun things that we've either referenced or some of the things that we didn't get a chance to cover. That's
okay.
it.
Yeah. Awesome. So in that case, we will go ahead and move on to the off topic. First, I will say for those of you who are here in the live audience, go ahead and if you've got any questions, go ahead and line them up in the chat. We've got a couple of people in line already. You can either type your question in the chat or you can put an exclamation point and that will line you up. You get to ask your own questions. We're not going to do any follow-up questions, and the questions must be on topic, brief, and courteous. All right, on to the off topic. So for those of you who are new to the Switch, we have a segment we like to call the off topic, where we ask our guests to bring up some topic that is not directly related to the main topic. It can be tangentially related, if you like. It can be serious, it can be silly, it can be lighthearted, it can be heavy. So, Stacy, Dad, what do you have for us?
My off topic generally, and I have some more specific, is photography.
Nice.
Yeah.
Okay.
So
I would say, well, anything in particular about photography? And the thing that I typically like to ask when someone brings up something like a hobby is, what is it that you get out of photography?
So I'll tell you what I get and what inspires me a little bit is I get to explore sort of the artistic side of things. I do believe that when I'm doing mathematics, there's a lot of artistic, even poetic thinking involved. But my day job, I'm doing a lot of programming, engineering type stuff. And I'm not really, I always say I'm not an engineer. And I'm a mathematician. Like if you ever watched The Big Bang Theory, there's Leonard, who's the experimental physicist. Sheldon is the theoretical physicist, and then beyond that you have the mathematician, who's even more abstract and weird than Sheldon. But we get to do a lot of creative stuff. But during the day, I'm doing a lot of programming, and there's some creative aspects to it, but it's not as artistic as I might like. And I've never been like a great singer or a great musician. I don't draw. Like I can see the thing in my head, but I can't really draw it. I haven't developed that skill, although I'm trying to teach myself a little bit. Photography gives me a chance to kind of express and capture moments of art. In fact, I had a picture that I was going to share with you I didn't bring up that kind of summarizes the inspiration that I get. The inspiration is from a photographer called Henri Cartier-Bresson. And his sort of famous quote, I'll say it in French, and I apologize if you're a French speaker if I butcher this, and then I'll say it in English, but he says, "Il n'y a rien dans ce monde qui n'est un moment décisif." In English, that means there's nothing in this world that does not have a decisive moment. In particular, he did a lot of what we call today street photography. And he would get out there and see things happening, and he would sort of wait for this moment that just crystallized it. So there's a really famous picture that he has of some kids playing and running, and one of them is leaping over this puddle, and there's like the splash and the reflection and the, whatever. But it's just like that moment captures the chaos, the joy of these kids playing. And he would kind of look at these scenes and just take the photos and just sort of wait for, okay, this is the thing, this is the photo that really grabs this scene, that captures it. So that's what, that's kind of what sort of inspired me, is that idea of, I want to capture images, but I want to capture the story behind the image. So the one that I have is actually, I took this at a parade many years ago, 4th of July parade. And I don't know if it makes sense for me to try to share that on the screen or whatever, but
Yeah, if
you
you
let me
can.
know. Well, I certainly can. And I guess for the people who are on the live feed, this would be great. For the people who are not, people who are watching this in video, we can kind of describe it, or who are not watching the video. Yeah,
If there's a way for us, if it's publicly hosted somewhere, we can put a link to it in the show notes, so that anyone listening afterward can at least pull it up.
Yeah, I'm not. I don't. I can. I guess I can share it publicly. And you got to tell me what you're seeing, because I see a big sharing bar on my screen.
I see it.
Okay, so yeah. So when you see that picture, it's and I kind of want people to just kind of get the story in their heads when they first see that. But here's this little kid wearing a Cub Scout uniform, and he's holding his arms straight up under this flag that's kind of got some waves in it. Giant flag, really giant compared to the kid. And he looks like he's just having an absolute blast. And all you see in the background are legs of taller people. There's, you don't see, way in the background, you can see some people kind of sitting on lawn chairs or whatever, but like mostly what you see is these legs sort of in the background. He's the only thing in the foreground. And for me, I was out there taking pictures of this parade, and most of them were kind of mundane. They didn't really capture the kind of the spirit of joy that I was seeing. And when I saw this little kid under the flag, just holding it up with his arms straight up in the air, I was like, yeah, that's it. That's got to be it. So I kind of traveled along with him for a few, probably a few dozen yards, getting myself positioned until I could just get it where I wanted it in the frame, and then just sprung right at that point to catch that photo. And for me, that's probably the closest I've come to that decisive moment in photography. I still try to do it. I'm not. I don't even pretend to be as masterful as some of these other photographers. I don't know how they get so many amazing images, and how they. I mean, these are folks, especially the ones that I really admire, who were using film cameras with limited number of exposures. They might have 12 or 24 or 36 exposures in the later years, but and it was film, and they couldn't look at it to go back and see, oh, did I get the shot, and I'll try again. They couldn't just upload it to a site and share it instantly. They had to go back and develop and do all this other stuff, and yet they were capable of getting these decisive moments. And that's kind of what drives me with photography, is this idea that you can capture some of this really amazingly cool stuff.
Yeah, that's incredible. I've always seen your photography and just been blown away by it, and it's cool to hear you talk about it in that manner. I've tried to pick up photography here and there, and it's not something I'm super enthusiastic about, but I have definitely felt the little tiny sparks of that feeling of, like, you get a shot that you're super happy with, and there's something really joyful about the whole process.
Yeah, I think it's really kind of cool. It's interesting to me that so many people, like pretty much everybody, I know there are people who don't have the means or the technology, but most of the people I encounter in the world today have smartphones, and they have cameras, and they take pictures. And it's funny to see how they just kind of throw the phone up in the air and kind of aim it in the general direction of the thing, and then they snap a picture. Most of those pictures never see the light of day again. People, oh yeah, I need to clean my phone up. I got 1,000 pictures on there. And I wonder how many of the 1,000 pictures they've ever looked at after the moment that they took it. And every once in a while, someone will get an image that they really love. They'll post it to Instagram, and like, oh man, you really nailed that. So it drives me a little bit nuts that people complain then about their equipment. Oh, I need the next XYZ phone. I'm not going to name a brand, but I need that next phone that's got the 5 cameras and the 87 megapixel thing. And I want to say to each one of those people, Bresson and Ansel Adams and all these great famous photographers, you have in your pocket a camera that is probably 10 times technically better than every camera they ever owned put together. Now, tell me why it is that you need that next 57 megapixel camera in order to improve your photography. It might be a great thing to have if you know what you're doing with it, if you know kind of why you need it, but it's not going to, if you go grab that thing and put it in auto mode and start taking snaps, it's not going to make your photography better. Understanding the principles of photography and the storytelling and those aspects of it will make your photography better. And I guarantee that Ansel Adams or Bresson could show up today with a 2 megapixel camera and blow away every picture you've ever taken on your iPhone. Oops, I said the brand. But they could. And the reason is that they understand the art and craft and not just sort of blasting at it. My other analogy, and I know I kind of rambled, my other analogy though is when people see a photo that I've taken and they go, wow, that's a really good photo. You must have a really good camera. Very few things raise my hackles, raise ire in me. But when people say that, I just want to throw something at them. Maybe something fluffy and light because I don't want to hurt anybody. But it's kind of like going to a chef and saying that meal, and I didn't come up with this analogy, someone else did, but that meal you made was absolutely amazing. You must have really good pots and pans. What? As if that makes the difference. Bobby Flay can cook in a tin can and outcook me. Bresson or Ansel Adams can shoot with a toy camera and take amazing photos. So that kind of stuff. That's why I love photography, though, is that it challenges me to push myself to that level of mastery I may never achieve, but I get to kind of pursue the masters.
It's interesting to me, being a musician, how different the intuitions I have around visual versus visual art versus music is, and how different people can have or not have one or the other. I have no intuition for pictures or how they should look. I can appreciate them, but if I go to take a photo, I don't know. I don't have the reference points in my head to really know what I'm going for. Whereas with music, I automatically know. I can just figure it out. So it's always interesting to appreciate a different form of art and learn about, like what you said, capturing a moment, capturing a story. It's and to kind of hear what different people get from other disciplines. So yeah, thanks for sharing.
I absolutely agree. And that's kind of why I challenge myself with it, because it's not something that comes really super naturally to me. Like mathematics was just sort of like, I just got it. It came really, quickly and easily. Photography is a challenge, and I need to push myself in something that I'm not naturally good at to get at least better. Whether I'm ever going to be good or great, I can't say, but at least I can feel sometimes that I'm improving. So, and I always post, like, of the many pictures I take, that's one of the things that I'm not on social media a lot, but on Instagram, it was funny. I actually had an Instagram account and I had probably 50 followers before I had a single post out there. Now I think I might have, I don't remember, 18 or 19 posts total. I don't know. There might be more than that, but not a ton of posts. But what I do is when I get one of those photos where I feel like that's worth sharing, that's a really cool image. There are a couple out there that I've shared just because they were goofy, but others that I thought were kind of fun. That's pretty much all I put on Instagram.
Yeah. If you don't mind, we'll link your Instagram in the show notes so people can
absolutely, yeah,
check those out.
Yep.
All right. Ready to move on to Q&A?
Sure. Yep.
Okay. We got a couple
I think we
of
lost
questions.
a ton of folks because we were way too heavy in the math for them, or it's too late tonight.
That's okay.
Yeah, it was a fantastic interview. I really appreciated this. I mean, it was really wonderful. It was riveting, and it was amazing how you were able to capture these concepts and communicate them so clearly. So, thank you. So, my question is kind of it's somewhat basic. It's not basic, but I've learned kind of a little bit more about graph theory from the 7 bridges problem.
Mm-hmm.
And so that was like a conceptual framework that it gave me to understand circuits and how things are connected to one another and how even social networks are related to or work to a certain degree. Can you recommend a resource that would actually explain graph theory in a little bit better, greater detail using similar types of concepts? Because this was like, something that really I just was able to grasp, and it was clear, and it really got me interested in a lot of other things, like, again, circuits. But if you can, that would be great.
I'm trying to think if I have a specific one. I know there are lots of graph theory. So it depends on how deep you want to go. If you want to sort of start with just sort of playing with some concepts, then I know that, again, going back to Martin Gardner and some of the mathematical games folks, there are a lot of books that have those. I have, and I tried to bring some of my, did I bring a graph theory book over here? I have a fairly good graph theory book from Dover Press. Let's see. Yeah. It may be across the room in one of my other sections. I believe it was Dover Press. Dover does a lot of these little sort of advanced, I would say, intermediate to advanced math books. Some of them are things like, introduction books, like Introduction to Linear Algebra and Differential Equations, and number theory and stuff. I don't know if they're still doing these, but I pretty much, when I was, as I was growing up, anytime we were in a bookstore, I would hit the math section, find those Dover Press books, and if there was one I didn't have, especially if they were on sale, I would convince my parents to get them for me, or when I got old enough to buy them myself. So I think theirs is pretty good. I think Khan Academy, the graph theory stuff there is pretty good. Not sure if I have any other great resources for you, but I would start with those.
Thank you.
Mm-hmm.
All right, next up, thanks, Joe. The next person is Sanjay.
Sorry, I had difficulty getting my microphone unmuted. So I actually have 2 questions. I don't know if I'll be able to ask both, but the first one, So both of them have to do with teaching math in the elementary schools. And so first, I had a comment, and I just wanted your thoughts on this. So I know that in elementary schools, not middle school or high school, elementary school, usually first, second, or third grade, in Europe and Asia, they actually teach early set theory to children, to young children. And I think that that's actually something that we should do in the US. I'm not aware of any school that does this in the US, other than there may be private schools. But I think it would really give a much better foundation for young students if we did that. So I just wanted to get your thoughts on that. And if I can, I'd like to ask a second question after that.
Yeah, sure.
Yeah.
We'll allow it. Go ahead.
Yeah, and I really appreciate that comment. I agree with you wholeheartedly. I remember when I was in grade school, that they were experimenting with something back then they were calling, quote, the new math. And it was basically set theory. They were teaching us set theory, and we were learning about intersections and unions, and we were seeing, Venn diagrams, and we had little blocks that we would play with to build out examples of it. And I do believe that it helps to get you in the mode of thinking abstractly, but with some concrete examples to help. I borrowed this term from someone years and years ago. I don't remember exactly who it was, but it's what I call sequential abstract thinking, sequential dash abstract. And the idea is that I present you with a concept, but in order for you to understand the concept, I need to give you lots of examples. That's the sequence part. So the sequential part is me feeding you example after example on top of my maybe limited explanations of the concept. The abstract part is when it clicks in your head, and now you can perform the abstraction. Now you get it. Like if I teach you about addition, and I do enough additions where you've done it over and over and over and over, and then finally it clicks in your head, oh, in my head, I know the general algorithm, I can add anything now. And I think set theory does that. It helps you with that kind of sequential abstract thinking in a way that is approachable and in a way that can happen faster than with some of the other more abstract things. So you're absolutely right. I believe that teaching set theory would really, really help. And second part, yes.
Yeah, actually, so I just on that point, when I was in first grade, I was in India, and I didn't realize that they actually taught us set theory. And one of the things I think that happened was that, or that happens when they do that to students, is that it forms, I mean, the way that our minds develop in terms of thinking about mathematics, it forms in a certain structural way, not physiologically, but basically the concepts and as you're describing, the ideas around math get formed in a certain way that helps throughout the rest of your math education. And so I think it is important to have these preliminary things. So the next question has to do with proofs. And again, in the US, most of the time, proofs are brought up for the first time, formally in geometry, which is usually second year of high school, and that's kind of late. So I'm wondering, why do you think we don't teach proofs at an earlier age? Because it doesn't have to be taught using geometry. It can be taught using other methods. And probably, I suspect it would help if we teach it at an earlier stage.
Yeah, it's a good question. I don't really know for sure, but my gut tells me that there are at least two reasons for this. One is that we underestimate the capacity of children. I believe that, and I know this because I taught kids who were 5 years old. This was many years ago. I don't want to give away too many, but many years ago, before we had the internet even. We were learning on Apple Mac computers and Apple IIs and things like that. Taught them programming and taught them some abstract thinking. We underestimate what they're capable of. If a 5-year-old can do the kinds of things that I was seeing, I'm sure they can handle some of the what we might consider more advanced math concepts. But so problem one is we underestimate what the kids are capable of. Problem two is that even if we said, okay, we're going to do this, we're going to push this idea, we're going to have the kids learn some of these things, many parents, especially in the Western world, in the US, are incapable of supporting that. So many parents would balk at the idea because it confuses them and they don't get it and they don't understand it, and quote, math is hard, why are you doing this to my kid? I mean, there's so many parents that complain that that what I thought was kind of simple math was way too hard for their kids, and were complaining that the schools were giving them work that was well beyond them because the parents couldn't do it. So I think you need to build that support system. And going back to what Laura was saying, the teachers need to be empowered better. The teachers need to be taught better. All of those things have to click into place before we can really go beyond that, where we can push beyond that. But I do agree with you that kids are capable of it. We just need to challenge ourselves societally to step up and to be able to do it.
I think that's an awesome sentiment to end on. We've been at this for about 2 hours now. It flies by.
Yeah.
That was awesome. Any closing thoughts?
My closing thoughts, I really appreciate everyone who joined, the people who stuck with it. I know it's a long slog through this. I know there are a few people who had to drop for various reasons, and I'm hoping that they'll go back and pick up the rest later. But you know, let's keep some momentum going with this type of thinking. And if people are interested, check out some of the links that are out there. You know, we may be able to get some more discussions going on this type of topic in the future of the show as well, or even in other meetups. But I definitely appreciated it. And yeah, that's it. Thanks, everybody.
Awesome. Well, thank you very much. If anybody is interested in following up with you, or they've got math questions or math ideas, or they just want to know more, I mentioned we'd put your Instagram in the show notes. Is there anything else you want to point people to where they can get in touch if you're open to it?
Yeah, I mean, I'm not really, I don't do a ton of social media. I have a Facebook account. I could say that much, but I'm really terrible at using it. I'm also on LinkedIn. I'm slightly terrible at that too. I don't know, maybe we can figure something out. And I guess I'll also put a link to my photography site on there as well. But I guess, you know, probably Instagram, you know, if you want to message me there, or, you know, whatever, that's probably a good way to do it.
All right.
And if we need to come up with a better way, we can do that. I can create an email account just for that if people are interested.
Sounds good. All right. Well, thank you very much for joining us on the Switch tonight. It was awesome. And yeah, I'll talk to you soon.
All right.
Yeah, thanks, Stacy.
Right. Good night, everybody.
Folks, okay, with this, I want to, Stacy.
Yeah.
I have a ton of questions. Okay.
Okay.
I've been very quiet throughout.
If you ask me to prove that Zorn's lemma is isomorphic to the axiom of choice,
no, this is what I'm proposing.
I will, but I'm going to have
This
flashbacks.
is what I'm proposing. It's a little late, but I'll tell you what I have in mind. And I would like you to come back either this weekend, either like 12:30 on Sunday or 12:30 on Saturday. Let me tell you what I have in mind.
Sure.
I had a researcher on polymaths this Sunday. He basically did a PhD on studying the how scientists think under Kuhn. And what he found was that what science is, when he studied the scientist, and he himself is a scientist, the process of doing science is nothing like what is taught as science. And the biggest problem, he was saying, is that the science teachers don't get it.
Right.
Of what science is. I think something, no, I know that exactly the same thing is happening for math for exactly the same reasons.
Sure.
Okay. So what I want to do is I want to do a whole meetup on that theme. So questions like, I want to elaborate on this point, the point that we learned from this gentleman. His name is Ruth Bernstein. He's one of the pioneers on research on polymaths. And he was pointing out that science and artistic thought are very closely linked. So that, that's another theme that I want to talk about, kind of math and the art, sense of beauty. So we would talk about, I see, this is something I've always struggled with. I have wanted to communicate to people what math is, because I don't think people get what math is.
Right.
Math is not what they learned, just like science is not what they learned. And it is very hard. I have tried to do it in multiple ways, but I think in conversation, we'll be able to make that clearer, at least point to where it lies for more people. So that's what I would like to do. And I have I have at least 20 questions already. I also one of the things I want to do is to look at what you described, the 8-queen problem, and how somebody who knows only arithmetic, whose conception of mathematics is only arithmetical, deals with the problem, versus somebody who is a mathematician, or who, in short, who knows algebra, deals with it. And what in principle is the difference in the approach and what it makes possible. So we'll use that as an example to kind of elucidate what mathematical thinking is, something like that. So I want to make it clear. So does Sunday, or this Sunday or Saturday work for you around 12:30?
I think both of them would. I think either one of them works.
Okay. Then I would prefer Sunday.
Okay.
I think Sunday integrates well with the meetups that we have.
Yeah.
So we'll do a meetup on that. And then what I want to do is that I want to take this, say, okay, what is mathematics? What is really mathematics, right? And then apply it to math education, because I know that that's your passion. I care deeply about that. And math education, not only for kids, but math re-education for adults as well, so that we can kind of show people what math is. So let's do that. So Stacy, this is excellent. I'm very excited about this. So
cool.
12:30 Eastern time on this Sunday.
All right,
folks.
Write it down.
Folks, please come back for that. I'll be announcing that shortly on Meetup.
Sounds good.
All righty.
Looking forward.
All right.
Sounds
Thank you
great.
very much, folks.
Thanks.
Good night, everybody.
Good night.